All right. So we are going to work on allele frequencies. All right. So our first population, we have 2,340 whatever bunny rabbits. And of those 2,340, 1,398 are homozygous dominant, 808 are heterozygous, and 134 are homozygous recessive. And what we want to know is in this population, and this is a later population, so we'll put this there. In this population, we want to know what percent are big A and what percent are little a. So the first thing I like to do is I like to go ahead and double our original population, because if this 2,340 whatever, bunny rabbits, squirrels, whatever, they each have two alleles, one from mom, one from dad. And so I want to multiply that number by 2, and that's going to give me my number down here. When I do part over whole, that's going to be my whole number. It's going to be on the bottom. All right, then I need to look at these. So these 1,398 will go with bunny rabbits. Each have two big A's. So that means for each one, there's two big A's. So I need to multiply this times 2, because each one of these bunny rabbits has two big A's times 2. So that is 2,796 dominant alleles in that population or that group. These 808 bunnies also have two alleles. One's a big A, one's a small a. So that means I have 808 big A's, right? Because they each have one big A, and 808 small A's because they each have a small a. And then these guys down here, there's 134 bunnies that are little. They have two little A's. And so I'm going to take that 134 times 2, and that is 268, and that is little a. Okay. And then you're just going to add these two together and add these two together, and that's what's going to be on the top, because I want to know my number of big A's over my whole, which was 4,680, my number of little A's over my total population of alleles. Okay, so I'm going to add these two together. I'll start with the big A's. 2,796 plus 808 is 3,604. I'm going to go ahead and divide it by the 4,680 since it's already on my calculator. Whoa, except I didn't divide. 4,680. And that gives me 0.77 or 77%. You can multiply it times 100, or you can just move that decimal point over 2 places. My other one will be 808 plus 268. That is 1076 divided by 4,680. And that is 23%. And I'm just going to round it to the nearest whole number. All right, so those were my allele frequencies in the original population. And now what I want to know is in this new population, has it changed? Has this population evolved? Something has killed off a bunch of my bunnies. I went from 2,340 bunnies to 789. So I don't know if predators came in or if a disease hit or what, but my population has shrunk drastically. But of these 789 bunny rabbits, they are going to have 1,578 alleles because each one has two alleles, right? One from mom, one from dad. Then, so that's going to be my total that's going to go down here at the bottom. All right, then we start looking at each genotype. So this genotype, 514 times 2, that's going to be 1,028 big A's. These in the middle are going to have 188 big A's and 188 little A's because they have one of each. And then these 87 have two little A's. And so that is 174 little A's. Okay, I'm going to add 1028 plus 188 is 1216. So that's 1216 over my total, 1578. And I'm going to go ahead and divide since it's already on my calculator. And that is 77%. It's looking like it didn't change, but we'll verify. 174. That is 362 over 1578. And that is 23%. And so because the numbers have stayed the same, So this was maybe in 1960 and this was in 2000 or whatever. They've stayed the same over time. Then we would say that this is not evolving. Or you could say it is in Hardy-Weinberg, I'll abbreviate that, equilibrium. Okay? Because evolution and equilibrium, Hardy-Weinberg equilibrium are opposites. All right, so let's look at another population. Okay, so this population, we'll say these are, I don't know, squirrels. This population, we have 246 squirrels. So those 246 each have two alleles, one from each parent. So that's a total of 492 alleles. Again, that's what's going to go on the bottom when we get down here. All right, these 76 squirrels have two big A's, so that is a total of 152 big A's, dominant alleles there. These 15 have a big A and a little a, so that's 15 big A's, 15 little A's. And these 155 that are little a, that is a total of 310 little A's, okay? So 152 plus 15, that is 167. That's the part over the 492, the whole. 2 is 34%. And then 15 plus 310 is 325. You don't have to write these numbers up here. I don't know why I am. I don't think I do that every time. And that is going to be 492, 66%. And you can kind of double check. I didn't say this with the other ones, but these two numbers should add up to 100%, or depending on rounding, maybe 101 or 99, but it should be really close. And that does. So we know that we did our math right. Okay, so that's, let's say this was in, I don't know, 1996. Okay, and then we came back in 2016. Okay, so 20 years later, and we saw the same population. They've grown lots more. Well, I can't remember what I said, squirrels. So we'll do 934 times 2. So that is 1,868 alleles. Again, that's the number that's going to go on the bottom. So I just do that first. You don't have to, you can do it later. All right, these 355 squirrels have two big A's each. So I'm going to multiply that times 2, and that is 710 big A. These 261 squirrels have a big A and a little a, so that's 261 big A's, 261 little A's. And then these 318 down here each have two little A's, so that is 636 little A's in those bunnies, squirrels, whatever. I forget what I said. I think I said squirrels. All right, so 710 plus 261, that is 971 big A's over 1868. And that is 52%. Okay, sorry, I was just, and that looks like a change because we were at 34. All right, and then doing my little a's, 261 plus 636 is 897 over 1868. 68 is 48%. Okay, so these did change. The big A dropped, increased, sorry, from 34% to 52%. The little a, 66, dropped to 48. So something is causing the dominant allele. Let's say this is, what did I say, squirrels? Let's say that dominant is gray and recessive is brown. Something is making the gray ones more likely to survive. Maybe they can camouflage better, and the brown ones have decreased. So they are dying. So we would say this is evolving because there is a change. And it is not in Hardy-Weinberg equilibrium. Okay, I hope that helps, but if not, let's talk about it in class. Bring your questions.